Okay, question 4.4. Well, it's asking which of the following systems are BIBO stable. So what is BIBO stable? If what is BIBO stable? Well, it's the BIBO actually is the acronym for bounded input, bounded output, and that's a system. Just consider a system like this, and consider the input is x of t, and the output is y of t. Okay. Well, a system is BIBO stable if the input is bounded, the output is also bounded. Okay, so if this is bounded, then this is also bounded. This is what BIBO stable means. But how can we find a system is BIBO stable? Well, there are many different solutions. Well, the main solution that works everywhere is you can assume that the input signal is impulse delta t. Okay, you can give this to the system, and when the input is delta t, then output becomes h of t. Okay, the impulse response. So this is the impulse, which is bounded because impulse is 1 if t is 0 and is 0 if t is not 0. So this is bounded. So you give delta t to the system and then check the impulse response, the response of the system to this delta t. If the response is bounded, then you find that okay, you can find that okay, the system is stable, otherwise the system is not stable. When the Laplace transform or transfer function of ht is given, when we have Laplace transform of h of t, which is h of s, when this is given, we can simply find h of t by Laplace inverse transform of hs. Okay, this is the main solution. But there is also a shortcut. And the shortcut says you can simply check the poles of the system. Okay. If all poles have negative part, then we can conclude that the system have negative real part. Okay. Then we can conclude that system is BIBO stable. So this is a shortcut. You don't need to find the ht and then find the inverse Laplace transform of hs. Okay, you don't need to do that. You can just check the poles, and if the real part of all poles are negative, just consider that all poles should have the negative real part. Then you can say the system is BIBO stable. Okay, so for this one, well, I want to check the poles. Here we have 3 poles. First pole comes here when s plus 2 is 0. So we can conclude s equals minus 2. So one pole is at s equals minus 2. I can do the same. The second pole is at s equals minus 3. And the third pole is where s equals plus 1. So what was the condition for a system to be BIBO stable? The condition is the real part of all poles should be negative. Well, this is true here, this is true here, but this is not true here. So we conclude that this system is not BIBO. Well, I think you can do the rest, but since we can quickly do that, then let's do it here. For the second one, we say the system is not proper. So I don't even check the poles because the system is not proper. Since the system is not proper, we conclude that the system is not BIBO stable. But what is a proper system? A proper system is a system that the degree of nominator to be equal or less than the degree of denominator. So you see the degree of nominator here is 2. The degree of denominator is 1 because s has power of 1, but here s has power of 2. So that means this system, it has another definition for improper for proper system is the number of poles. So the number of poles should be more than or equal to the number of zeros. Well, you see that this doesn't match here because we have 2 zeros here. We can have 2 zeros here or 1 zeros here, but we have 1 zeros, s equals minus 5. Okay, so probably I should change this to larger than. The number of poles should be more than the number of zeros. So this system is not proper. So when the system is not proper, the system is not BIBO stable. And let's check this one here. Well, the number of poles, we should check the poles. Well, one pole is at s plus 3 equals 0, and that's s equals minus 3. Well, the real part of the pole is negative, so that's fine for this one. But I should also check the poles at this one. And when I want to check poles for this one, I should first check the root of this polynomial. The roots, we should check for the roots where this polynomial equals 0. So let me write it here. We have s2 plus 2s plus 5. Okay, we want to see where this polynomial equals 0. The roots of this polynomial is the poles of this transfer function. Well, I use quadratic equation, quadratic formula, and the quadratic formula says that the roots for a polynomial like this is minus b. Well, since it is at the order of 2, I can use quadratic equation, quadratic formula, and that says for a polynomial like as2 plus bs plus c equals 0, the roots are, there are 2 roots. One root is minus b plus a square root of b squared minus 4 times a times c, all divided by 2 times a. This is one root, and the second root is the conjugate of this, minus b minus square root of b squared minus 4ac all divided by 2a. Okay, so let's calculate this, the first one. Well, here b is 2, c is 5, and a is 1. Okay, so we have 2a, which is 2 here, and minus b, which is minus 2, plus the square root of b squared, which is 4, minus 4 times 1 times 5, which is 20. So this equals minus 2 plus minus 16 over 2. Okay, how can I solve this? This doesn't have a real answer, but it has imaginary. Well, we know that 1j imaginary or complex number actually is the square root of minus 1. Okay, and that means j squared is minus 1. I use this to write it here in the form of complex numbers. So we have for a square root of minus 16, I can write it like the square root of 16 times j squared, or I can write it in this form, j squared, which is minus 1 times 16. Okay, and this well equals j squared 4 squared. Okay, now I can cancel the square root and the squares here, so this equals j4. Okay, if I replace that here, then we would have minus 2 plus j4 time divided by 2. I can do the same for this, but I don't need to go all the steps then, so I can write, because you know, just the plus sign here is changed to minus, so I have minus 2 minus j4 over 2, which is minus 1 minus j2 here, and for this one I can write it, I always have problem with this, I don't have much space, so this is minus 1 plus j2. Okay, so this is one of the roots, one of the poles we found. This is another pole we found here, and another pole here. We have totally 3 poles for this transfer function, 3 poles. And if you check the poles, because we're gonna see if this system is BIBO stable or not, okay? If you check the poles, you see that the real parts of all poles are negative. And that means the system is BIBO stable. Let me write it down here. All poles are minus 1 minus j times 2 and minus 1 plus j times 2. This is all the poles for this transfer function. And if you check, you see that the real part of all poles are negative. The real part here, the real part there are negative. Okay, so we've done that for question 4.4. So let me stop the video. Okay, part D. We want to find the poles in this transfer function. So take this polynomial s squared plus 5. I want to find the poles for this transfer function. So that means I want to find the roots of this polynomial. Okay, so if I solve this, then I have s2 equals minus 5, and that we can conclude s equals plus minus the square root of minus 5. And we know that this can't be a real value. Okay, this is a complex value. So consider j, we know that equals the square root of minus 1. Okay, so j squared is minus 1. That means I can write s equals plus minus of, instead of minus 5, I can write it like j squared times 5. J squared is minus 1, so this equals -5. Agree? So okay, so that is this square root and the square here, these two cancels each other. So I can write this as plus minus, because there are two possibilities. It can be either plus square root of j squared times 5 or minus square root of j squared times 5. Either of them makes s squared plus 5 equal to 0. So we have then j, because square root cancels the square there, j times square root of 5. Okay, so we have two poles. So for this, poles are either j square root of j times square root of 5 and minus j square root of 5. Okay, so if I want to write this as in a format of a rectangular complex number, then it is 0 plus, okay, 0 plus j square root of 5, or 0 minus j times the square root of 5. And you see that the real part here is 0, and the same here, the real part is 0. And as I said, if a system wants to be BIBO stable, then its transfer function should have the real part of poles of its transfer functions should be negative, which is not negative here. So that means this system is not BIBO stable.